You want to know everything about projectile motion? Or finally build your own cat cannon? Very good. Then you are in exactly the right place. Welcome to Physics with Lucky. Today we are talking about projectile motion, and we are going to derive the so-called trajectory equation. And if you also thought the cannon was kind of funny, feel free to leave a like. We use a coordinate system in which y describes the height and x the distance from the starting point. Since we want to discuss the general case, our launch point is located at an arbitrary height h. That height can of course also be 0 or negative if you bury the cannon in the ground. The red point mass m stands for the cannonball, the dart, or whatever else you intend to throw or launch. In the end, however, the mass will not matter, because, strictly speaking, we are deriving these equations only for the vacuum case. Since we will need them later, let us write down the initial conditions right away. At time t equals 0, the x-coordinate of the projectile is also 0, as you can clearly see in the coordinate system. And the y-coordinate is equal to h, we just established that. Then we still need a launch velocity. And that is this vector v0, pointing at an angle alpha relative to the x-axis. The trajectory, which is described by the trajectory equation, then looks roughly like this. So yes, already pretty parabolic. Let us call the range r. Then we can also write down the final state. After the flight time tf, the x-coordinate is equal to r, even though we do not know those two values yet. And the y-coordinate? Well, that is of course 0, because after the flight time, the projectile has reached the ground. First, let us look at which forces act on the projectile after launch. No forces, no dynamics. Well, the only force is gravity acting downward. There are no other forces. So Newton's second law simply becomes Fg equals m times a, and is therefore identical to the free fall. But since we now have motion in 2 dimensions, we cannot restrict ourselves to the vertical motion only. If we write out the vector equation, we get in x direction 0 equals m times a, and in y direction minus mg equals m times a. So the acceleration in x direction is 0, and the acceleration in y direction is the gravitational acceleration minus g. So far not very surprising. Lucky wants us to split the entire motion into its horizontal and vertical components. For the acceleration, we have already done that here. Let us continue directly with the initial velocity. This also has 2 components, v0x and v0y. To determine them, let us take another look at the sketch. The velocity vector initially points upward, and usually one specifies a launch angle between the vector and the horizontal. We called this angle alpha. The 2 components, v0x and v0y, are the horizontal and the vertical projection of the vector v0. What we now have in front of us is a right triangle. So we can use the definition of cosine, that is adjacent side over hypotenuse, and sine, that was opposite side over hypotenuse, to write down one relation each between a component and the magnitude of the velocity vector. The magnitude, that is the length of the velocity vector, is of course defined by the Pythagorean theorem. At this point, you are probably asking yourselves, why are we doing all of this? Well, we assume that we know the launch velocity, that is the magnitude of the velocity vector, and the launch angle alpha, but not the components of the vector. But those are exactly what we need in order to split the motion into horizontal and vertical components. And with our 2 formulas, we have now achieved exactly that. Depending on how we change the launch angle, its cosine and sine change as well, and with them, the components of the velocity vector. Now we have everything we need to solve the equations of motion. We begin with the horizontal motion. The horizontal acceleration ax is 0. The velocity is the integral of the acceleration over time t, and the integral of the number 0 is just some constant c1. So the velocity is constant, of course. That is exactly what we expect if there's no acceleration. And if it is constant, then it is of course always equal to its initial value. So throughout the entire motion, the velocity is simply equal to the initial horizontal velocity v0x. And we just determined v0x. That was v0 cosine alpha. The next we are interested in is the horizontal position x as a function of time t. The position is the time integral of the velocity, and since this velocity is constant, this is simply initial velocity times t, plus another integration constant c2. If we plug in t equals 0 here, we get x of 0 equals c2. And x of 0 we already wrote down right at the beginning. And that was the horizontal starting point, and that is 0. So c2 is equal to 0. And if we insert v0x, we obtain the horizontal equation of motion. This is the equation of uniform motion. After all, v0 cosine alpha is ultimately just a constant. The vertical motion is slightly more complicated, because here the acceleration is not 0. Otherwise, however, we proceed exactly as we did for the horizontal motion. The velocity is the time integral of the acceleration, giving minus gt plus an integration constant. If we plug in the time t equals 0, we find that c1 is once again the initial velocity, only this time the vertical component of it. We insert that, write it out, and obtain the vertical velocity as a function of time. The vertical position is the time integral of the velocity. We can solve that directly and again get a constant c2. If we once more plug in t equals 0, we get y of 0 equals c2. But y of 0 is the initial height h, so c2 is h. We insert that, and if you want you can rearrange the terms a little, but this is really a matter of taste. In any case, we obtain here the equation of uniformly accelerated motion. And we are done. With the equations x of t and y of t, the kinematics of projectile motion are completely described. So we could stop here. But we will not. Back in the intro, I promised the trajectory equation. And that is what we are going to deal with now. So far, we have the x-coordinate and the y-coordinate of the projectile as functions of time. But the trajectory equation describes the path y of x starting from height h. Lucky is giving us another sketch for this. If you generally like the sketches, both of us would be very happy about a like. And if you have suggestions for improvement, feel free to leave a comment as well. Okay, so how do we get the trajectory equation? Somehow we have to get rid of the time t and combine the two equations. To do this, we start with our equation of motion for x and solve it for time t. Then we use the equation of motion for y and insert this t. That is a great trick because actually at this point we already have it. What we now have is an equation y of x that no longer contains any t. This equation can still be simplified a little if you know that the ratio of sine to cosine is equal to tangent. And that is the trajectory equation. It's a parabolic equation. Do not let all the trigonomic functions confuse you. Once you plug in alpha, g, v0, only numbers remain. And then you simply have an ordinary quadratic equation with one coefficient in front of x and one in front of x squared. The coefficient in front of x squared has a negative sign, so the parabola opens downward. But you can already see that anyway. Lucky has prepared another animation here for the trajectory equation. And it is almost worth a subscription by itself. We now follow our point mass along its trajectory and observe both velocity components live. And you immediately see that the horizontal component Vx does not change. The vertical component, on the other hand, first points upward, then becomes smaller and smaller until it vanishes completely at the apex, only to then grow again downward. That is simply the effect of gravity. The fact that the vertical component vanishes at the apex will become important again later. Lucky, remember that. How long is the projectile actually in the air? We can calculate that easily, because we know that at the end of its flight, the projectile touches the ground, so the height at the end of the flight time is equal to 0. We plug the flight time tf into the vertical solution of the equation of motion and directly see that tf is the root of a quadratic function. And that is calculated with the quadratic formula. If we insert v0y here, we obtain the general solution for the flight time. We choose the solution with a positive root because only that one gives a positive value for the flight time. Lucky thinks I should also write down the solution for the case when the initial height h equals 0. No problem. 2gh would disappear from under the square root, and then the square root and the squares underneath cancel nicely, leaving 2v0 sine alpha. Also a nice result. And how far does the projectile go if you launch it at a certain angle? Here we proceed similarly to what we just did. The range r is simply the x position the projectile has at the end of its flight, that is, after the flight time has elapsed. So let us insert tf into x of t. Now we use the general solution for tf that we just derived, insert v0x and pull the g out in front. And finally, we also insert v0y. And with that, we have the general formula for the range. Here too there is a simplified solution for the case initial height h equals 0. In some cases, it is interesting to know what maximum height the projectile can reach. The maximum height is reached at the moment when the maximum height is reached. That does not sound very helpful, I know. I will gladly take the like for the joke anyway. Clearly, that only helps us if we know the time. But there's a way to determine it. If we remember the animation with the velocity vectors, it was the case that the vertical component vanished at the highest point, right, Lucky? Vy at Tmax is therefore equal to 0. So we insert Tmax into Vy and solve for Tmax. Done. Now we can insert Tmax into y of t and calculate Ymax. Multiplying everything out leads to a strong simplification of the expression. If we then also insert v0y, we obtain the general equation for the maximum height. A very common question is, what is the optimal launch angle to maximize the range? This time we split the answer right from the beginning into two variants. One for the special case initial height h equals 0 and one for initial height h is not equal to 0. For initial height 0, we begin with the corresponding formula for the range as a function of angle alpha, and we want to know for which angle r becomes maximal. This is what is called an optimization problem, and you solve it by taking the derivative with respect to alpha and setting it equal to 0. We solve the last step by means of the mathematical technique of looking closely. When does dr by d alpha equal 0? That can only happen when the cosine of 2 alpha becomes 0. And when is cosine 0? Well, at 90 degrees. If 2 alpha has to be 90 degrees, then alpha itself has to be 45 degrees. Makes sense, right? Okay, now for the general case, h is not equal to 0. I have to admit, I looked into it and the derivation is relatively cumbersome and would make this already rather long video even longer. So even though Lucky is probably angry right now, I decided to simply write down the result without derivation. If anyone in my loyal 8-person community is actually interested in the derivation, then feel free to write it in the comments. Last but not least, we want to derive the general formula for the maximum range. The maximum range is the range the projectile reaches when you launch it at the ideal angle. We again begin with the trajectory equation and consider the situation at the end of the flight at x equals r. There, the projectile is on the ground, so y is equal to 0. If we plug that in, we obtain an equation that still contains the angle alpha. And that is exactly what we actually want to get rid of. For that, we use a little trick. We replace the tangent of alpha by a new variable u. In addition, we use that 1 through cosine squared is equal to 1 plus tangent squared. If we plug that in and rearrange things a little, we obtain a quadratic equation in u. And now comes the crucial point. For a given range r, there's only a real launch angle if this quadratic equation has a real solution at all. And that is exactly the case when its discriminant is greater than or equal to 0. But for the maximum possible range, we are exactly at the limiting case. So at the point where there is just barely still a real angle. That means the discriminant must be equal to 0. So that is what we now impose. If we write out the discriminant, we initially get a somewhat strange expression. But after expanding and combining terms, the whole thing simplifies surprisingly strongly. In the end, we are left with an equation that we can solve directly for r squared. And if we then also take the square root, we obtain the general formula for the maximum range. So that is the result. You can see very nicely, the greater the initial velocity, the greater the maximum range becomes. And the greater the initial height h is, the farther the projectile also travels. So that fits exactly with what one would physically expect. If we set h equals 0, the corresponding term simply disappears, and for the maximum range we obtain v0 squared over g. And that is exactly the result we would also expect for the special case with optimal angle 45 degrees. So now we really do have everything important about projectile motion together. And with that, we are done for today. Lucky is satisfied for now, at least halfway. Because of course there are still many things one could add that we deliberately left out today. For example, air resistance. Then the motion in x direction would no longer be constant, and almost everything would become much more unpleasant. Or wind, or an altitude-dependent air density, or a changing gravitational acceleration if your cat cannon is designed in a very ambitious way. But for the kinematic understanding, today was exactly the right altitude. If you enjoyed the video, feel free to leave a like, subscribe to the channel, and write in the comments which topic we should tackle next. See you next time.